Welcome to another episode of the Distributed Data Show, brought to you by DataStax Academy, where we bring you the latest news and interview technical experts to help you succeed at building large-scale distributed systems. Hello everyone, the Distributed Data Show, back in the studio today with DuyHai Doan. How are you?
I'm fine. Hello, Patrick.
So we have a little more of a heady topic today. We're not going to talk about a specific technology like Cassandra or Solar or anything else. It's going to be about techniques. And the topic is
partitioning techniques in distributed systems.
Of course. So you and I both, we tell people about how to use distributed systems, and using them means understanding them.
Exactly.
Yeah, and then when you don't understand them, what usually happens?
Catastrophe.
Yeah, it's bad. It's really, really bad. So partitioning techniques. Now, when we talk about that, maybe you can explain what a partitioning technique is. Why is this important?
So basically, when we talk about distributed system, we are talking about multiple machines cluster, right? If you have single machine, you are not a distributed system. And when you have multiple machines, you need to put data on all of them. Mm-hmm. The question is, how do I distribute my data on all those machines? And then come the partitioning techniques.
So I think a lot of folks that come from relational land know about sharding.
Yeah.
And sharding, of course, is when you take data, you break it into pieces, and then distribute it across multiple machines. Mm-hmm. That, it's similar, but it's not the same topic, right?
It depends on, because the sharding is a subset of partitioning techniques.
Okay, all right. So in more modern distributed data systems, all of that's handled automatically, correct?
Yeah, more or less.
Right.
You have some system where you only choose the columns on which the algorithm of partitioning is applied to.
Right.
You don't decide which algorithm. The system imposes you the algorithm. You have some system where you are freely, it's up to you to choose how you distribute your data. Mm-hmm. So those have pros and cons, right?
Right.
And in fact, we have two distinct families of partitioning scheme.
Yeah, so what are the, that's a good place to start, is let's break this into the bigger pieces. So what are the two largest pieces of how to distribute data in a distributed system?
So you have two ideas. The first idea is I want to spread out my data evenly. So the best way to do that is to introduce randomness and to use hash function. You apply a hash function to some of your primary keys, and then depending on the hash value, you know on which machine you should assign your data. The second family is range-based partitioning. So this family is really simple to explain. Let's say you have a column, and it is a text column or an integer value. So you would say, okay, from 0 to 10 for this column, I will assign my data to node number 1, for 10 to 20, node number 2, and so on.
Right. So all right, let's dig into each one of these, and I think we'll leave the hashing one for the last, because that's the most interesting one, and there's a lot to that. Let's talk about one that may be a little more familiar: range-based partitioning techniques.
Yes. So for the key thing is, so let's talk about pro and cons. Right. The pro is when you partition your data by range of values. The key thing is you can have range queries, of course. What does it mean? It means that first you can access your data by equality. So give me, for example, user where user ID equals to some values, or hash of user ID equals to some value. Or you can say, give me all the user where user ID is between 10 and 20. So inequality queries, right? It is very convenient. The cons is now you risk hotspot. Because how can you be sure that for each range of data you will have the same amount of data?
Yeah, so I think that when sharding, when you're sharding a database, which is a range-based partition and very difficult to get right, if, for instance, if you use letters of a last name.
Yeah, exactly, like this.
Yeah, then you're not going to have a statistically even data set.
No.
Because, yeah, and then especially when you're in certain geographies where, names may start with M, like mine, quite a bit, and then none of them are starting with X.
Exactly.
That there's difference. Even with IDs, and I've seen this happen too, where because you're generating sequential IDs, that's very difficult to do as well, because now you have to find, I've seen this before where range-based queries would fill up a machine and then get to a certain limit, and then they'd start filling up a new machine.
Exactly. And also, I would like to stress on the point that when you choose range-based partitioning, you are facing sooner or later hotspot. So most of the technology who are choosing range-based partitioning, they have what they call rebalancing.
Right.
The rebalancing process, okay, at some point in time, I realized that some machine has more data than others. So I start to move my range of values to rebalance those data. But rebalancing has a huge cost. Usually people don't realize it. What does it mean in practice, rebalancing data? It means reading data out of disk, so disk I/O cost, read them into memory, pull them on a network, so network will be busy, and at the receiving node, serializing them and writing them back to disk.
Yeah, there's a lot of activity that has to,
and
moving data is never cheap.
Exactly. And in fact, you have two choices. Either you can trigger the rebalancing manually. So it is an operator who decide, okay, okay, my traffic right now on my cluster is very low. I can just trigger a rebalancing, fine. But it puts a lot of manual work to the operator. Or you can decide to do it automatically.
Right.
But then you take the risk in the middle of a heavy traffic to start a rebalancing.
I would also say that this is where there's the other problem that I've seen, and most of the range-based algorithms that I've seen are very much in the application. The application has to be aware of it and has to guide it. Now, I have seen some others. For instance, with Cassandra, we had byte-ordered partitioner, and the byte-ordered partitioner was that it used a range, and then it divided the range into how many nodes you had. The hotspot problem was the issue there. I had a friend who used to say this all the time: use BOP and your ops people will plan your disappearance.
Exactly.
It's not good.
And also we even didn't talk about all the issue related to rebalancing, because what are your guarantees about consistency when you are moving data? Right. Because in the middle of moving data, the data has not lived yet the sender node, and the receiving node have not received all of them yet. So in terms of consistency, should I query the sender node or should I query the receiver node to get the data?
Right.
And imagine that the rebalancing failed in the middle. What do? Do we roll back? Or do we just retry? So see, you open
you hope your data is immutable. That's what you hope for. Item potency for the win. Which is another advantage inside Cassandra land, is that the item potency of that data inside of the data model itself really helps whenever you have these kind of problems. And that's harder to do with the relational databases. It's actually almost impossible. Okay, well that's range-based partitioning. How about the more interesting one, the hash-based partitioning?
So hash-based partitioning, as its names imply, we use a hash function.
A consistent hashing algorithm.
Yeah.
Yes.
So the idea is not to take any random hash function, because the idea here is to have a very good distribution of your data. So your hash function should be very distributive. And right now, in the state of the art, the most distributive hash function out there is Momo 3.
Right.
We are using in modern Cassandra cluster. So the pros is that you are guaranteed to have a good distribution of data. So I want to warn all of our watchers. The guarantee of good distribution is statistical. What do I mean? Imagine you are playing rolling dice, right? You roll a dice 6 times. What is the guarantee you have 1, 2, 3, 4, 5, 6? No guarantee. You can have 3 times number 1, 3 times number 2, and that's all.
Well, it's a non-repeated trial too.
Exactly.
Right.
So the guarantee to have good distribution of data with the hash-based partitioning is you should have a lot of distinct value.
Large N, yes.
Yeah. So the more you have distinct value of the partition keys you have, the better the distribution is.
Yeah, that's pretty critical. And again, with the consistent hashing algorithm, and I think this bears some explanation, it's not just a randomizer, it's really like a one-way door. You put a string into it, and it will always give you the same hash.
Yeah.
Random hash, but the same one. So if I put in DuyHai, it spits out a huge 64-bit or 120-bit, whatever size you need from your hash, but it'll always spit that out. And if you put in a Shakespeare sonnet, it'll spit out a 64-bit hash, but it'll always be that hash.
The same, yes.
And that's actually a pretty incredible thing. And the limit on collision at that point is, well, theoretically there is a potential for collision in the universe. But with such a huge number, I think the chances are
very small, extremely small.
Yeah, and that I think that's where a lot of people get hung up. Wait a minute, isn't there going to be a collision, or is it going to have my data overlapping? Probably not.
Yeah.
Actually, no, it won't happen.
And of course, now those are the pros, and the cons are now because you are applying a hash function on your partition key. Now you can no longer query your partition key by range. Because in fact, when you hash a value, you lose the ordering.
Right.
Because the hash value are completely distributed all over the range of possible values. So.
Yeah, it's scattered out.
Exactly.
And if you need any kind of sequence, then you're going to be bouncing around all over the place to find that.
But in fact, the trick is there is an ordering, but the order is on the hashed values.
Right.
Not on the original value. So in fact, for you, developer, knowing that the hash value of your partition key is order, well, it doesn't help really. The only moment, the only case, the only scenario where it's useful is you want to perform a full scan of your table, and you do it by chunk. So you can say, okay, I start with the hash value being -2, blah, 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 and then you move on sequentially, and then you can apply the idea that the hash value is order.
And
but
that's
it's
how
the only moment.
Yeah, and that's how you know you're getting all of the data for a particular node in that distributed system partitioned by a consistent hash. But it doesn't give you the guarantee that the data in the partition key that went into the hash is ordered. So if it's 1, 2, 3 and gets hashed in different ways,
exactly.
That's not the point of that. So like Cassandra and CQL, there's a function getToken that shows you the token value for that partition key. And that partition key is what we're talking about. That's how it gets distributed throughout the Cassandra cluster. But that getToken will give you a number that is on a particular node.
Yeah. And
you can range through those token numbers and get every bit of data on that node.
Exactly.
By the way, that's kind of the secret how the Spark stuff works, which is not a secret, but I think it's still pretty interesting.
Yeah.
Have you seen, I'm kind of loading the question here a little bit, but have you seen some newer things in computer science about partitioning techniques, or some more modern thinking around what a partitioning technique looks like in a large distributed system?
The idea of, so you can introduce some idea where you have a bit of your data which is fixed, and introduce some hashing. Part of your data, part of your primary keys is hash. Part of your primary key is on them you can perform range query, but it is what we already have in Cassandra, right?
Right.
Partition keys, clustering columns. One part of your primary key is for distribution, the other part is for range query.
Right.
And in fact, in those kind of new techniques, it's very hard because whenever you touch the hash function, you lose ordering.
Yeah.
So that's the key. It's a mathematic property.
Yeah, and you can't break math.
No.
You
cannot really find a hash function that guarantee you strict ordering. No, it doesn't exist. It's not a hash function anymore.
I've seen some interesting ideas around hybridizing it or finding ways to control some order, get some order control. Google had an interesting paper not too long ago about around load. So using an ordered-based partitioner, but with load shedding in it, you're starting to get into much more advanced, much more complicated hashing techniques. And that, I think that's interesting, and it may be something that develops over time. But the simplicity of a consistent hashing algorithm or range-based partitioner, it really is helpful, because when you're writing code, let's say you're building an application for some company or for yourself, you don't want to have to spend a few days on the math.
Yeah, you don't need to have a PhD on computer science.
You just want to write your code.
Yeah.
Right. Well, this has been really interesting. I mean, I hope it has been interesting for you too. I could talk about distributed computing for hours, and I'm sure you wouldn't want to listen to that. And you could too, couldn't you?
Yeah.
We have before, many, many times. Well, thank you very much for joining me today, DuyHai.
Thank you, Patrick.
All right, and thanks everyone for joining us on the Distributed Data Show. We'll see you next time. Thank you for joining us again for the Distributed Data Show. We love your feedback, so go to the Distributed Data Show page on DataStax Academy and tell us what you think. You can also find us on the DataStax Academy YouTube channel, or find our podcast on iTunes, Google Play, or wherever you get great podcasts. While you're there, make sure and subscribe so you don't miss a single episode.